In this video, we'll be talking about how to solve exponential and logarithmic equations. Let's start off with the exponential ones. An exponential equation is one in which the unknown variable is in the exponent. Exponential functions are one-to-one. This means that if a to the power of x is equal to a to the power of y, then x must equal y. In other words, if you have two bases that are raised to an exponent and the bases are the same, the exponents have to be the same. Let's see how this becomes useful when solving exponential equations. Example 1 wants us to solve each of these equations and provide exact answers, then round to 3 decimal places if necessary. In part A, we have 2 to the power of x is equal to 64. So there's a few ways that we can go about thinking about this. I have 2 to the power of x is equal to 64. 64 is a power of 2. And so it is equivalent to 2 to the 6th power. Since our bases are the same here, we must have that the exponents are equal. And so this implies that x is equal to 6. Now, I could have solved this a little bit differently. Since we are learning about logarithms, I can also use either the common logarithm or the natural logarithm, really any logarithm I choose. I'm going to go with the natural logarithm here. And we learned about the logarithm laws, so my exponent, I can bring that out. And now if I'm solving for x, I can divide both sides by natural log of 2, and that will give us the natural log of 64 divided by the natural log of 2. So notice here I went ahead in my calculator, typed in natural log of 64 divided by natural log of 2, and we can see that that is equal to 6, just like we got previously. So again, this is equal to 6. All right, let's move on to part B. I have 7 to the power of x minus 1 is equal to 7 to the power of 5x plus 9. Now, because these have the same base and exponential functions are one-to-one, I must have that the exponents have to be equal to each other. So I have 5x plus 9, and I can subtract x from both sides. That will give us 4x is equal to, and then I could add 1 to both sides, and that would give me 10. Then if I divide both sides by 4, we get x equals 5 halves. Similarly, in part B, I could have used a logarithm, so let's see how that would have worked. So we have 7 to the power of x minus 1 is equal to 7 to the power of 5x plus 9. If I wanted to, I can apply log base 7, or really any log base, but 7 is going to make it easier, because if I were to use the power rule, I could bring out x minus 1, and then I'd have log base 7 of 7, and this is equal to 1 by definition. And then similarly here, I could bring out 5x plus 9 times log base 7 of 7, and again, this is equal to 1. So that's how logarithms are related too. We could apply it to both sides. We would get the exact same answer. Let's move on to part C. In part C, again, we have the same bases, so I'm going to set the exponents equal to each other. And from here, I'm going to add x squared to both sides. I'm also going to add 1 to both sides. That's going to give us 2x squared is equal to 2. From here, I can divide both sides by 2 and get x squared is equal to 1. By taking the square root, I end up getting x is equal to plus or minus 1. And if we plug in either of those back into the original equation, we will end up getting the same answer on both sides of the equation. So these are going to check out. So my solutions here are -1 and +1 for part C. In part D, we once again have the same bases. So I'm going to set my exponents equal to each other. This is going to turn into a quadratic equation if I add x squared to both sides. So we get x squared minus 3x minus 4 is equal to 0. This is a quadratic that I am able to factor. it will factor into x minus 4 times x plus 1. And if I use the zero product principle to set each of my factors equal to 0, we will get x equals 4 and x equals -1. All right, I think I made a small error in part B. Let's go back. I'm going to subtract x from both sides, and I'm going to subtract 9 from both sides. So that's going to give us 4x equals -10. And then if we divide both sides by 4, we get x equals -5/2. So my apologies, let's go back and fix that. This should be -5/2. All right, let's move on to part E. In part E, we don't have an exponent on the right-hand side, so this is going to work slightly differently. I'm going to first start off by dividing both sides of my equation by 3. Now, something that I want to emphasize is I will often, when I ask students what we should do as a first step here, every once in a while I'll get the answer that we should multiply the 3 and the 2 together to get 6 to the power of x is equal to 42. This is very wrong because of order of operations. 2 has an exponent on it, and so if we were following PEMDAS, we would need to apply the exponent first, which is why I can't multiply my 2 and my 3 together. But what I can do is I can divide both sides by 3. That will give us 2 to the power of x is equal to 42 over 3. And is 42 divisible by 3? I think so. So 14. Great. So we have 2 to the power of x is equal to 14. 14 is not a power of 2, so I'm going to use a logarithm at this stage. And again, we can use any logarithm base we want to. In this scenario, I'll use the common logarithm, and now I can use the power rule. So on the left-hand side, I can bring out my exponent. I'm going to have x times log of 2 equals log of 14. And then from here, I will divide both sides by log of 2. That's going to give us x equals log of 14 divided by log of 2. Now, this is an exact answer, and if you're taking a quiz or an exam and it asks for an exact answer, this would be our final answer. It does tell us to approximate then to 3 decimal places, so I'm going to go ahead and do that. This comes out to being about 3.807. All right, let's move on to part F. I'm going to start off by subtracting 4 from both sides. If I do that, we'll get 5 times e to the power of x is equal to 62 minus 4 is 58. Then from here, I'm going to divide both sides by 5, and we get e to the x is equal to 58 over 5. Now what I'm going to do is I'm going to apply the natural log to both sides. And because on the left-hand side we have a base of e, we're just going to be left with x. And we get x equals the natural log of 58 over 5. So there is our exact answer. And then as a decimal approximation, this comes out to 2.451. So that completes our first example here. All right, let's go ahead and move on to our next example. Example 2 wants us to solve the equation e to the power of 2x minus 3 times e to the power of x is equal to -2. I'm going to start this off by adding 2 to both sides of my equation, which will end up giving us e to the power of 2x minus 3 times e to the x plus 2 is equal to 0. Now, this is something that I like to do by substituting in another variable. If you don't want to do it this way, that's totally fine. I think it makes it easier to see that this ends up looking like a quadratic. So I'm going to say let w equal e to the power of x. And why are we doing that? Well, if I rewrite my first term in my equation here, I can rewrite this as e to the power of x quantity squared. Those are the same thing based off exponent properties. Minus 3 times e to the power of x plus 2 equals 0. Now what I can do is e to the x here, I can replace that with a w, and then e to the x here, I could replace that with a w, and doing so will give me w squared minus 3w plus 2 equals 0. And now this is a quadratic equation that we can solve using factoring. So this will give me w minus 2 times w minus 1 is equal to 0, and we end up getting w equals 2 and w equals 1. Now be careful, our original equation was in terms of x, which means that we need to solve for x here, and right now we've solved for w. So sometimes students will forget to substitute back in the original variable, and they'll think that 2 and 1 are our final answers, which is not the case. So I want to replace w with what we originally defined it to be, which is e to the x. And now we want to go ahead and solve these two equations. And this one, the value of x that makes that true has to be 0. You could take the natural log of both sides, but the natural log of 1 is 0. So we end up here getting x equals 0. And then for this other equation, I can take the natural log of both sides, and that's going to give us x equals the natural log of 2. And so plugging these both back into our original equation is going to make things work out. So these are our two solutions. They are 0 and the natural log of 2. And those are our exact answers. If you want, we could approximate the natural log of 2, and rounding it to 3 decimal places, it comes out to about 0.693. And that concludes example 2. Example 3 wants us to solve the equation e to the power of 2x minus e to the x equals 6. We're going to solve this equation very similarly to how we solved the last one. So let's subtract 6 from both sides. That's going to give us e to the power of 2x minus e to the x minus 6 is equal to 0. I'm also going to rewrite the first term like we did last time as e to the x to the power of 2. And once again, I'm going to say let e to the x equal w. So our new equation becomes w squared minus w minus 6 equals 0. I'm going to factor this now into w minus 3 times w plus 2 is equal to 0. From here, using the zero product principle, we'll get w equals 3 and w equals negative 2. If we substitute back in for our original variable, we're getting e to the x is equal to 3 and e to the x is equal to negative 2. Now, if you thought about graphing y equals e to the power of x, that's going to look something like this. It's an exponential function. I know that there is a horizontal asymptote on the x-axis, and my graph is not going to cross the x-axis or touch it, and negative 2 is down here, so this graph will never have a y value of negative 2. So all of that is to say that this equation here has no solution, so we're not going to get an x value out of that. This one, it does have a solution. I can take the natural log of both sides. That would give me natural log of e to the x is equal to natural log of 3, and this left-hand side ends up simplifying to be just x, and we get x equals the natural log of 3, and this is our final answer. Let's check by plugging it back in really quickly. I would have e to the power of 2 times the natural log of 3 minus e to the power of the natural log of 3, and we want this to end up equaling 6. So let's see if that happens. On my first term, I can use the power rule and bring this 2 inside of my natural log. So that's going to end up being e to the natural log of 3 to the power of 2, which is 9, minus e to the power of the natural log of 3. And remember, the natural exponential function and the natural log are inverses of each other, and so they will kind of undo each other, if you will. So this is going to end up leaving us with 9 minus 3, which is equal to 6. That's what we wanted because we have 6 here and 6 here. So the solution that we found is valid and it checks out. Let's move on to talking about logarithmic equations. A logarithmic equation is one in which the unknown variable is inside of a logarithm. Some logarithmic equations can be solved by using the fact that logarithmic functions are one-to-one. This means that if you have a single logarithm equal to another single logarithm and they have the same base, then their insides have to be equal. Be cautious, this only works if the two logarithms have the same base. Example 4 says, solve each equation, provide exact answers, then round to 3 decimal places if necessary. In part A, we have the natural log of x is equal to 7. Now, there's a couple ways we can think about this. If you've seen a previous video of mine, the way that we've defined logarithms, or one of the ways, we have log base b of x is equal to y, and assuming that the logarithm comes first or on the left side of the equation, I say that we can use bay, where b stands for base, a stands for argument, and e stands for exponent. And bay is a mnemonic device to help us to rewrite this in exponential form. So b is our base, y is our exponent, and then x is our argument. And so bay is just a way to rewrite this in exponential form. We can apply this to part A, where we have the natural log of x is equal to 7. And remember, if we have the natural log, there is an assumed base e there. So b-a-e, and we can say that we have e to the power of 7 is equal to x, and this would be our final answer. But where does bay really come from? Well, let's see an alternative to solving this. Another thing that we can do is we could have e represent the base of both sides of our equation, and that's okay as long as we do the same thing to one side as to the other. And then what happens on the left-hand side is we're just left with x, and then we have e to the 7th. And so same idea as bay, just, a slightly different flavor. All right, let's move on to part B. All right, so in part B, I'm going to apply a similar idea where I'm going to have 4 be my base on both sides. And because 4 to the power of something and log base 4 are inverses of each other, these kind of undo each other or get rid of each other. And so we're left with 5x minus 1 is equal to x plus 7. But similarly, because these have the same bases and they're equal to each other, we can use this idea here. So that means that the inside of this and the inside of that have to be equal to each other. So we are here. I'm going to now subtract x from both sides. We get 4x minus 1 is equal to 7. I can add 1 to both sides, and we get 4x is equal to 8. Then from here, I could divide both sides by 4, and we get x is equal to 2. In part C, we have log base 6 of 3x plus 14 minus log base 6 of 3 is equal to log base 6 of 2x. Now, on the left-hand side of our equation, we have two logarithms. Luckily, they have the same base, but in order to proceed, what's going to be helpful in this scenario is using our logarithm laws. So if you haven't seen that video, go back and watch it on logarithm laws, but I can condense this thing here into a single logarithm, and that will become log base 6 of 3x plus 14 over 3. So right now we're using the quotient rule for logarithms, and this is equal to log base 6 of 2x. Now that I have a single logarithm on each side, and notice that they have the same base of 6, now I can take my insides and set them equal to each other. And if it helps you, again, you could have 6 be the base of both sides. These will undo each other, cancel each other out, and so we are left with 3x plus 14 over 3 is equal to 2x. From here, I can multiply both sides by 3. That will give us 3x plus 14 is equal to 6x. Then I can subtract 3x from both sides. We'll get 3x is equal to 14. And finally, we can divide both sides by 3, giving us x equals 14 over 3. So that is our final answer for part C. And that concludes example 4. Example 5 wants us to solve some more logarithmic equations and provide the exact answers, then round to 3 decimal places if necessary. In part A, we have 5 plus 2 times the natural log of x equals 4. I'm going to subtract 5 from both sides, which will give us 2 times the natural log of x is equal to -1. Then if we divide both sides by 2, we get the natural log of x is equal to 1/2. From here, I can e both sides, and that's going to get rid of that. So we get x is equal to e to the -1/2 power, and that is our answer for part A, which is approximately 0.607. Part B, we have 2 times log base 5 of 3x is equal to 4. I'm going to divide both sides by 2. That'll give us log base 5 of 3x is equal to 2. I'm going to have both sides be the exponent of the base of 5. That will get rid of that. And so we have 3x is equal to 5 squared. And if we divide both sides by 3, 5 squared is 25. Then if we divide by 3, we get that. So here is our final answer for part B, and here is our final answer for part A. All right, in part C, we have log of 5x plus log of x minus 1 is equal to 2, and we want to condense this into a single logarithm, and again, we need a logarithm law, and the one that we're going to use is the product rule for logarithms, which will allow me to condense this into a single logarithm. Please make sure that you are putting parentheses because I need to distribute the 5x into both the x and the minus 1. If we do that, we get log of 5x squared minus 5x, and this is equal to 2. Now at this point, again, we could either use Bay, or because we're using the common logarithm, the base is 10, and we could do that. Those will undo each other. And so we get 5x squared minus 5x is equal to 10 to the power of 2 is 100. Now if I subtract 100 from both sides, this ends up changing into a quadratic equation. We love those. So I'm going to factor out 5. Notice that every term is divisible by 5. So that's going to leave us with x squared minus x minus 20 is equal to 0. I don't need that 5, so I'm going to divide both sides by 5. These will cancel out, and then this becomes 0. 0 divided by 5 is 0. So let's clean this up and see what our new equation is. So I should be able to factor this now into x minus 5 times x plus 4 is equal to 0. That's going to give us x equals 5 and x equals -4. Now, this is why it's important to always check for extraneous solutions, because if I were to plug in x equals 4 in for x right there, that's going to give us log of -4 minus 1, which is equal to log of -5. Remember, we cannot take the logarithm of 0, and we also cannot take the logarithm of negative numbers, which means this thing here is an extraneous solution. So for part C, our final answer is just 5. In part D, we have log base 2 of 8 plus log of 3 minus 4x is equal to 2. Now, in this case, we can't use one of the logarithm laws to help us out because the two logs on the left side of our equal sign do not have the same base. But luckily, log base 2 of 8 is a number that we should know without a calculator. This ends up being 3 because 2 to the power of 3 gives us 8. Now I can subtract 3 on both sides. And now we could do this. These will cancel or undo each other. And we have 3 minus 4x is equal to 10 to the negative 1 power. And 10 to the negative 1 power, that is the same thing as 1/10. And I want to get rid of fractions, so I'm going to multiply everything by 10. That'll give me 30 minus 40x is equal to 1. Now I'm going to subtract 30 from both sides. That'll give me negative 40 is equal to, oh, don't forget the x, negative 29. Then I can divide both sides by negative 40. So we get x equals 29 over 40 because the negatives undo each other. So we have 29 over 40 as our solution for part D. All right, so we have in part E, log base 9 of 4x squared plus 5 minus log base 9 of 5 is equal to 2. I'm going to combine that into a single logarithm using the quotient rule. And now I want to get rid of the logarithm, so I can either use Bay or this idea. And we're going to get 4x squared plus 5 over 5 is equal to 9 times 9, or 9 squared is 81. And then what can we do from here? Now I want to multiply both sides by 5. I had a student ask me yesterday, can we do this and cancel out the 5s? And my answer to that is absolutely not. Please don't do that. You could only do that, or another way of thinking about it is you'd have to break this up into two separate fractions. And in this case, 5 divided by 5 is in fact 1, but you still need to divide the other term by 5. So you could simplify this to 4x squared over 5 plus 1 like that, but otherwise, no, you cannot do that. Okay, so I want to now multiply both sides of my equation by 5. These will now divide out, and we get 4x squared plus 5 is equal to 81 times 5, which is 405. Then I can subtract 5 from both sides. That will give us 400. Then I can divide both sides by 4. I get x squared is equal to 100. Take the square root of both sides, and we get x is equal to plus or minus 10. Now, we can plug in both of these because in our x value, we're squaring it, and we don't have to worry about taking the log of some negative number. So these are both valid solutions. All right, let's move on to the next example. In part F, I'm going to want to use the quotient rule for logarithms. I'm going to combine this into a single log. Now, because these logs have the same base, I can just set the insides equal to each other. We get x minus 5 over x minus 3 is equal to 28. I can multiply both sides by x minus 3. That will give us x minus 5 is equal to 28 times x minus 3. And so if I distribute the 28, we get x minus 5 equals 28x minus 84. I'm going to subtract x on both sides, and I'm going to add 84 to both sides. So then we get 27x is equal to 79, and then divide both sides by 27, and we get x equals 79 over 27. Now, if you throw that into your calculator, this is approximately 2.926. And if you were to take this, specifically the 2.96, and throw that into that x value, you're going to end up getting a negative number. Remember, we cannot take the logarithm of a negative number. So it turns out that for part F, there's no solution. And remember, for no solution, there's a few different ways we can denote that. You could write the empty set. You could put a set of curly brackets with nothing inside. That's also the empty set. Or you could also write no solution. So I would take any of these, whatever your preference is. All right, for part G, we have log base 2 of x squared minus x minus 2 equals 2. And I'm going to put a 2 here and a 2 here. So that's going to get rid of the logarithm for us. And we get x squared minus x minus 2 is equal to 2 squared, which is the same thing as 4. Now I'm going to subtract 4 on both sides. We'll get x squared minus x minus 6 is equal to 0. I'm going to factor this. If you check both of those answers, or both of those x values into the original equation, it should become true. So those are our negative 2 and 3 is our solution set. Let's move on to the next one. All right, for part H, I'm going to go ahead and e both sides, and then that will give us x plus 2 quantity squared is equal to e to the power of 6. I'm going to go ahead and expand out my left-hand side. That's going to give us x squared plus 4x plus 4 equals e to the power of 6. And now I'm going to subtract e to the 6 from both sides, and we're going to get x squared plus 4x plus 4 minus e to the power of 6 is equal to 0. And remember, 4 minus e to the 6 is a constant. Even though e is a letter, it's a constant, it's not a variable. And so this now becomes a quadratic equation, and I can use the quadratic formula. So our leading coefficient a is 1, our b value is 4, and then our c value is 4 minus e to the power of x. So if we use the quadratic formula, we get x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So now what we do is let's simplify our radicand, or our discriminant. 4 squared is 16, and then 4 times 1 is just 4. And I'm going to distribute this into my parentheses. So I get minus 16, and then plus 4e to the power of 6 all over 2. 16 minus 16 is 0. And then we can take the square root of 4, that's 2, and then the square root of e to the 6 is e cubed. So we get x equals negative 4 plus or minus 2e cubed over 2. And we could factor out a 2 from the numerator. These 2's will cancel out. And so finally we get that our answers are negative 2 plus or minus e cubed. Okay, so I went ahead and also rounded those to 3 decimal places. I just wanted to address as well, you might be asking, why were we not able to use the power rule for logarithms? So here I have this as my original equation. Why can't we bring the power on the outside? Well, let's do that. So I have 2 times the natural log of x plus 2 is equal to 6. If I divide both sides by 2, then we get the natural log of x plus 2 is equal to 3. And then if I e both sides, then we get x plus 2 is equal to e cubed. And then if I subtract 2 from both sides, we get x equals negative 2 plus e cubed. So you could do it that way. It's just only going to give you one solution. So you have to be mindful that there's actually two solutions. And using the power rule only gives you one of them. All right, this concludes this video. Thanks for watching. See you next time.